Okay, good morning. Today we continue the chapter 14, which is partial derivatives, and next week we are going to have midterm, okay, midterm exam. Friday, topics will be chapter 10, 11, and 12, but 12 only the last part, the quadratic surface. The one that we need to, sometimes we need to sketch and draw, or maybe we have some equation and we need to know like what that equation will turns out in the three-dimension curve. Okay. So questions like the model, like in our quiz yesterday, those kind of questions with the same level of difficulty, perhaps it will also show up in the midterm. Okay. So I hope within this week, or perhaps as early as possible before Wednesday, I hope I can give you some answer key, and also if not answer key, maybe the last year midterm answers. Okay. So if you want to check the midterm, I have prepared in the middle, I think last week or a few days ago. You can check those questions in the Moodle. Okay. I think some of the questions similar to what we have in quiz, and it's like a typical problem. Like, for example, finding the radius of convergence, interval of convergence. That is pretty typical. That and I emphasize that before our quiz, that it must be like it should be at least one question about that, right? And I think in the midterm maybe there will be a question like that also, perhaps. And also about the Maclaurin also, it will come up. So if you think memorizing the formula in Maclaurin can help, then you can try to find a way to memorize. Yeah, I think it's easy to see the pattern between the functions and the pattern, function series. Okay, now we are going to see for today's class. I will just focus on the chapter 14. Maybe if we want to review our midterm, maybe on next week, either maybe on Wednesday next week, I will review for midterm. But now I'll focus on chapter 14 first. Okay, which we have here is the tangent plane. So basically, if we know our function z equal function of xy, we can try to rewrite our tangent plane equation. So z minus z0, okay, the difference in z equal to the partial x at that point. And remember, this partial x and partial y, their role is as the slope, actually the slope of the t. It's the slope here. But since they have two slopes, they are making a plane, so that's why we call it tangent plane. So at this point P, we need to put in the point, okay? Point P based on this xy, okay? And then we are going to have the tangent plane. Let's get into some exercise, some example here. This is a simple example to show you how it works. So if we want to find the tangent plane, to the elliptic paraboloid, I hope you still remember the name. If not, you can check the function. So elliptic paraboloid z equal 2x squared plus y squared. Okay. Now, if z is constant, you'll see that this will be an ellipse, right? X squared, y squared, a constant ellipse, right? And if I cover y squared, we have parabola. If I cover x squared, we have another parabola y squared. Okay. So cover this y squared, cover this x squared, which means that is parabola on the other side. And on the xy plane, we have an ellipse. Okay, so I hope you can visualize, imagining, using your imaginations and try to work out the equations. That is elliptic parabola. So we want to find the tangent plane at the point 1, 1, 3. So 1, 1, 3 is x, y, and z, right? So x equal 1, y equal 1, and z equal 3. We can start by taking the z with respect to x or y to take our partial x and partial y. So partial x is, we are going to derive with respect to x. So this will be 4x. And y will be 0 because we treat them as a constant for x, right? And then partial y, we have 2y, okay? So 4x at x equal, or at the, let me write all the points 1, 1, 3, but we need just to make sure x is equal 1, put inside. Then fx is 4. And same thing with partial y. We put the point 1, 1, 3, which means that we just need y inside. So partial y is 2, okay? And then since z is 3, so this will be actually x0, y0, and z0, right? So z minus 3, or let me write the whole equation first, is equal partial x minus x0, plus partial y, and then we write z minus 3 for x minus 1, plus partial y is 2, y minus y1, minus 1, okay? And then simplify and solve this. So minus 6 plus 3 is minus 3. Okay. So this will be the tangent plane. Okay, if you see from the screen here, this is the elliptic parabola, and that is the tangent plane. Okay. So if you check using GeoGebra, this is one example. Okay. So in xy, if you look, this is ellipse, right? If this is the z and x, it's a parabola. And if the z and y, it's another parabola, okay? So I hope you can make this image in your mind, okay? So by doing the tracing, okay? Because for sure, one of the question, maybe some question in your exam, with the midterm, will be asking to, for example, if this is z to x squared plus y squared, you will see that if we close this, it's parabola. Okay. If we close this, it's another parabola. If we take this as a constant, it's an ellipse. Okay. you could see some possible arrangement. Like we have several structure, right, that has this kind of structure. Let's say we can have like z squared and then plus x squared over some constant, maybe plus y squared over another constant. This is maybe some constant here. Let's say a. This is another type of structure, right? You will see that this is ellipse, ellipse, another ellipse. So it's all ellipse all around. Okay. So I hope you can identify from the equations. You can identify what kind of structure you will have. Okay. And also, I hope the name. Okay. You see, we have parabola, and then an ellipse. So elliptic, paraboloid. Okay. You get the parabola having at least two possibilities. And then that is our tangent plane here. Okay, this tangent plane. Okay. And that's our tangent plane. Because it's on 1, 1. So this is 1, 1, and then 3 will be here. So this will be the point. So this is 3, and then this 1, 1 is around here. Okay. If you want to play around, try GeoGebra, try the 3D visualization, and you can just put every equation you can pick up. Okay. It's really helpful. Okay, back to the okay, so this is the plane. Okay, I've showed you how it looks like. And now on the bottom of the plane, so let's say we make our so let's say, suppose that this is going to be the plane that we show you, but we turns a little bit, so it's going to be downwards like this. So we can see some image that if we look at this scale, so that 4 and then maybe 4t on z, we see that perhaps it's the more we see, so you can see the point is in the middle here, right? The point at 1, 1, let's say 1, 1, 3, and then the more far you move your finger, you have a gap here, right? And if we change the scale, maybe make it smaller, and then let's zoom in. We zoom in, the gap smaller, right? The gap smaller, and you see that if we make another zoom in the middle here, nearby the point, we see that the gap getting smaller. The gap getting smaller. It's getting closer. And you will see that when we move, again, zoom in this part, we are going to see that we are going to see the plane and the curve or the surface. It will, maybe if we are because we have some limitations out in our eyes, and sometimes we have limitation in the image in pixel. We see that it kind of like they are the same thing, right? It seems that they are the same thing. So my conclusion from this picture is, if we are just looking at the nearby point that is close to the point where the tangent plane is, it means that we can somehow approximate. Okay, approximate. So we could approximate the point nearby. So the tangent plane is, from the last time, is 4x plus 2y minus 3. So let's write z in terms of L, which linear approximation. So we can write as Lxy. L stands for linearization, is equal 4x plus 2y minus 3. So what this L means? L means that if we put some point that is nearby the 0.113 that we mentioned in the question, it means that we can somehow approximate. Okay? For example, or let me write here. So we say that this is linearization, means that it's a good approximation to a function xy when xy is near 0.11. Why 11? Because we deal with that questions, right? So this is the tangent plane. So this is tangent plane to z equal to x squared plus y squared at 113. Okay, this 1 from here. So we see that this is 1. So we can approximate the surface with the tangent plane. Okay. So for instance, at let's say 1.1 and 0.95. I think this is quite close with the 0.11, right? Then we can just use linear approximation. So instead, taking it into this elliptic paraboloid, we can take this to this. But I don't think it's helpful. But if you are not using calculator, maybe helpful if you use this. So we can approximate this with 1 plus 2, 0.95 minus 3, which is approximate around 3.3. If you use the real value, so f anyone bring calculator? Can you calculate this? 2 multiplied 1.1 squared plus 0.95 squared. .3225. So I think it's quite okay, right? The approximation quite okay. So 3.3225. Okay. So it's I think it's quite close. I think quite close. Okay. And the more we get closer, maybe we can take 1.001, and this will be 0.99. Maybe we'll be getting better results, okay, and now closer to the real value. Okay. So we can use that into this form linearization and linear approximations. I don't want you to memorize this. This is the same thing as we did, okay, to find the tangent plane. And basically you change the functions, or you use the tangent plane to calculate the linearization. Okay. So basically it's the same thing. This is the tangent plane, right? This is z, this is z0, right? Z minus z0 equals this. That's the tangent, same tangent plane. right here the tangent plane. So basically they're the same thing. So okay, so linear approximation, right? Okay, so still in the linear approximation, we can also get into the differentiability, or in this case, the differentials. Okay. So we can write the differentials, or maybe let me write. Maybe make. It's not differentiability. Differentials. So basically, differentials is we are going to write the difference in z as a delta, which we getting a smaller and smaller ratio, or the delta is getting small. This delta here we can write as a d, or the relative notation that we usually write as a so the delta z is going to be dz when it's very, very small. Okay. So we can write in terms of delta. And when the delta is getting closer to 0, 0, then this epsilon, the small distance between, it will also getting 0. In which we can simplify this just like we did in the tangent plane. So they are basically the same. Okay, this is how we prove through some epsilon definition. Okay, through some epsilon definition. The same with calculus 1. So it means that this delta means so delta z it represent change of value of f when xy changes from point AB, and then it changes some small distance delta x and delta y. So by taking this and by taking the delta closer to 0 means that the partial derivative exists near the point AB. Okay? And if they are also continuous, then the function will be differentiable at AB. So we can also write this theorem that if this partial x, okay, so they are going to be exist if they exist in this or nearby this AB, they are continuous at this AB, and then we can say that they are going to be differentiable at AB. And so they need to be exist and continuous. How to know whether the partial derivative exists? We have to go back to the limit definition of partial derivative. What's the limit definitions? Limit definitions for each x and y. For x, you change the x, y fixed. For partial y, you change y, but x fixed. It means from the limit definition from here. This is for the calculus one. So this is in calculus one. Calculus two is we will have x plus some let's say h and then y, and then this will be fxy. This is for partial x. This is just for first derivative. And this is for partial y. Sometimes you can just write h or delta, things the same meaning. Now it's going to be y that needs to change. Okay. So if we want to know whether it exists or not, we go back to the definition. Okay. Go back to the definition. Maybe it's correct differentiability, maybe differentiability, not differential. Why it's green? wait, maybe. I mean, I don't know why the cable is so sensitive. It's and then another thing to see is the continuous. Okay, continuous. So if you see any, so when you derive the partial, if it is not continuous, then it will not be differentiable at that point. Okay. Okay, that's differentiability. Okay, and then yeah, now this differentials. Okay, now differentials. So this is differentials in calculus 1. So this is in calculus 1, in which we start with defining that dy is f prime, or dy dx is f prime x, or we can write dy as f prime x dx. Now these forms we call the differentials. Okay, and how we could see that differentials is basically the change in the height. Okay, so this is the dy. It's basically for the tangent. Okay, but we have the delta, in which delta means the change with the curve. Okay, with the point. So we have a point here. So we have a delta and we have a d, in which they have differences, right? So we could make some error measurement. Okay? Is our approximation getting closer to the real value or not? So differentials within the using the tangent line and also the this dy and the delta, it could help us write or measure the changes and the error. Okay, basically. Okay, now in the partial, we are going to have these differentials. Okay, we can write this, or just simply dz is dz dou x dx plus which basically this is the same thing as the tangent plane again. We can think d as a delta, but very small. So d is the delta that is representing not the curve but the tangent. So dz, you can think like z minus d0. Dou z dou x, the x should be x. This dou z dou x is the partial x. The x is, you can say this is the delta, x minus x0. Dou z dou y is the partial y, and dou y is dy is the y minus y. So again, this is a tangent plane. But since we are taking the differentials, which means we are making the delta very small, we write the delta as d, which represent the tangent plane directly. Okay, the tangent plane directly. So basically, so this is calculus 1, only 2 dimension. In calculus 2, in our course, this will be what it looks like for the dz. So dz is actually the height between the tangent plane, okay? And for the delta, it's actually the surface to here. To this point, okay, the point that we find, okay? The point that we observe, okay? Let's say we observe at AB, so z is equal to FAB here. At this point here, so this AB, and point P point here. And we have the tangent, we have the surface, and we have the tangent plane at this point. Okay, this is the tangent plane, and this is the same thing again. The tangent plane. Okay, so we rewrite the tangent plane and write as differentials dz. So z minus FAB is our delta, partial x, and then this is the dx, the delta x, and then this is the partial y, that dou z dou y, and y minus b is the delta y. Okay. And again, by taking this, we can at least measure like how much differences between the plane and the real value. Okay. So again, it's also related to the linear approximation, whether our approximation is considered accurate or maybe close to the real value or not. Okay. So if you are maybe having some equations, for example, let me write equation here. Maybe make it smaller here. Okay, let's say we have if, so example, if z is function of xy and z is equal x squared plus 3xy minus y squared. First is find differential dz, and second, if x changes from 2 to 2.05 and y changes from 3 to 2.96. Compare dz and the delta. Okay, so basically find dz is take differentials. So this is going to be differential. So basically we are going to take partial derivative. Okay, take partial derivative. So dz is dou z dou x dx plus dou z dou y dy. So we are going to take partial with respect to x. So we have 2x plus 3y, right? 2x plus 3y here. And then dx. And plus, we take 3x, right? 3x minus 2y. And then we can take at so the dx, we can put 2 minus or 2.05 minus 2 is 0.05, and dy we can put 3 2.96 minus 3, or this will be equal to negative 0.04. Okay, so by taking this, we can take dz. So at x equal 2 and y equal 3, then dz is 2 multiplied by 2 plus 3 by 3, and dx is 0.05 plus 3 by 2 minus 2 by 3, and then negative 0.04. So plus 4 plus 9 is 13, and 5 is 65. 65 over 100, 0.65. 0.65, and this will be 0, right? So this will be 0. So it's 0.65. So the z, right? But the increment, the real value, the delta z, is basically f 2.05, 2.96 minus f2, 3. We have to put back into the original equations. So this will be 2.05 squared plus 3 and then minus minus 2.96 squared, and then minus 2 squared plus 3 minus 3 squared. Okay, I think I'll just show you the result is let me just write what is the result here. Okay. So it's going to be approximating the real value. So basically this is another way to write in more clean, to write the linear approximation. Directly you can write, this is also approximation. The same thing is tangent plane. Okay? So like I hope like you can see some observations that they're actually the same thing, but we are discussing that this is from different perspective. Okay. But basically, it's the same meaning. So whenever you find like linear approximation, differentials, tangent plane, they are the same. Okay, they are the same. Just like in calculus 1, you have tangent line and linear approximation, and they're actually the same thing. Okay, that's it for the tangent plane. Okay, maybe any question first? Okay. Yes.
You said which one is the approximate value?
This one.
Okay.
But the way we use differentials to approximate is more direct approach, which means that this is an exact value. Exact value. We can like definitively say, okay, this is an exact value from the differentials. So differentials is one way to make our calculations more specific. If we write just in terms of linear approximation like before, not in terms of differentials like this, we need to like writing this is approximate. The f is approximate some value which is in linear. But basically, in principle, they are the same thing. Like they are the same tangent plane, the same tangent plane. This is how we write. Differential is more precise, and you can just say that okay, this is equal to this because we already derived this in the differentials form. Right? Okay, so the difference between linear approximation, differentials, and the tangent plane is the way we write. Basically, they are the same thing, but the way we write it makes different. But the point itself, like if we observe some point, they are the same points. Okay. Okay, I think we can take a break if you want. Okay. It's already almost 9, so we are taking a break for a while. On the tangent plane, linear approximation, and differentials. Let's continue to the next part, which is the chain rule. Okay. So chain rule. So before I explain what is chain rule, so why it's actually called chain rule? Anyone knows why? Why it's called chain rule? Why does it look like a chain? So basically, to give you an impression why it's called chain rule, so you know how. Okay. If you remember in chapter 10, you should remember, okay, because next week midterm. So if you remember the, we can write like for example we are going to have like dy dt like this. We can write this as dy dx multiplied with dx dt, right? Okay. And basically, this is what we call chain rule. So imagine that we have more than, like maybe more than this. Like for example, let me write again dy dt. And in another case, okay, dy dt, let's say dy du, okay, and then du dphi, okay, and then dphi dx, and then dx dt. Okay, we have many variables, and we still can do this. And this is how chain looks like, chaining, okay? So it's like a chain. You're chaining all until we get what we have here, dy dt, okay? Now, in the chain rule for the partial derivative, we are not only chain rule only one variable, but we also have another one, okay? So, for example, here, what we did in the partial before, and if we have, for example, okay, we start with z equal function of two variables x, y, okay? And then we have x is function of t, y also function of t. Okay? So it's g of t and h of t. Okay, but g and h doesn't matter. But we know that variable t will be important here. Okay? So if we are going to partially derive z with respect to t, it means that we can derive the f with x and then derive x with t. And then this will be, you'll see that if we cancel this, it's dou f dou t, which is this, right? If we see the right one here, dou f dou y, dy dt, is basically dou f dou t, which is this. Okay, this is just one example. I don't want you to write this. Okay, this is still in the introduction. I will use another one that is, and another case. Okay, another case. Z is two variables. Okay, x, y, and then x, two variable s and t. So new variable. Y also have s and t. Now we could write the first one. We derive partially with respect to s. We get dou z, dou x, dou x, dou s. And then you see that if you cancel this, the same. Okay. This one also dou y, dou z, dou s, the same. Okay. This one also the same. This is also the same. Okay. So we are seeing some. Actually, a pattern. Okay, a pattern. Okay. So, how many variables you have for each part of it? So we start from z in top, and then z has x, y, and x and y has sd, sd. Okay, so we can somehow we can track this for the second one here. We can track here as x, y, and from x, y we have SD, SD, okay? And the first one also, we can write Z has X, Y, and this is D, this is D, okay? So this will be over here. So this will be dou z, dou x. This is dou z, dou y. This is dx, dt. This is dx, dy. And this is dou z, dou x. So every time you have a branch like this, then it means it's partial. It means we write the curvy d or the Leibniz notation or dou. Okay. So this is also partial. But if we have only one like this, we write with the d, and we write with d just to differentiate what that is. So this will be dou x, dou s. This is dou x, dou t. This is okay. So this is called the tree diagram. Okay. So in general, we can write the chain rule with variables infinitely. Okay, we can have more and more variables. Like we can derive this like u and ti, and then all the terms can be 1, 2 until n. Okay. So we can have like more and more variables to show that we can chaining all the conditions. Let me give you an example, okay? If you are, it's like a playing puzzle, like a puzzle, okay? So if we have the definition, so for example, if we have z is two variable x, y, and x may be a function of u, v, and y is h, another u, v, okay? Find chain rule for dou z, dou u, and dou z dou v. Okay. Now imagine that it can have more. It can have more, but our goal is to set up all these functions in terms of tree diagram. I think this is a better approach. Okay? You can start from the top, which defining all the positions. So you see that z is function of xy, and xy is another function. So we start from z. Okay? We start from z. We start from z on the top. Let me make it bigger. Z becomes x, become y, right? So it's branching, and then x become u, become v. Y also the same, become u, become v. Now each branch will get into, so z and x become dou z dou x, okay, and this one dou z dou y. Okay. And for the rest of it, we can start, this is x and u, this is x and v, this is y and u, and this is y and v. And basically, the way we are going to connect z, like partial z with respect to u and partial z with respect to y, is basically we are going to make a way, make a route or path. So dou z dou u means that a path from z to u. Okay, get it? So z from here, okay? And u is, we have two, this and this, right? Which means this dou z dou x multiply with dou x dou u plus dou z dou y multiply with dou y dou u. Okay, I think it's quite easy, right? If you are not getting it, really bad. Okay, so dou z dou u will be dou z dou x multiply with dou x dou u plus dou z dou y dou u. Okay, so let's, this is the line, this is the line, this is the line, this is the line. Okay, and you can imagine that if we have more, like this is only like branching on the two levels, right? Only two levels. We can have many levels, but as long as you can keep the principles, like from the start z and then the end, you need to choose what kind of chain rule you want. Okay, now we can do the same thing for dou z dou y. So dou z dou y, we can do the same thing. We start from z and then move out. Oh, not y, sorry, v. Dou z dou v. And then we ends up in v. So it's like a play a game. Okay, then that's why we have this two structure as mentioned on that one. And I think this is a perfect, like, symmetrical, right? But sometimes, depending on the case, depending on the function, sometimes maybe x only just have until here. X doesn't have any related with this one. Sometimes, so we can just add like and up to here. Okay, so it depends on the function. It depends on the function. Depends on the function. It's not always like really branching like a beautiful tree and then perfect symmetrical. It can also be not symmetrical. Maybe giving you some example, okay? Some examples so you can try do it by yourself. and then also reviewing partial derivative in general, okay, to make sure that we have completed this chain rule. Okay. Okay, so let me give you example here. Okay, so example, if z is x squared y plus 3xy with power of 4. Okay, x is sine 2t and y is cosine t. Find dz dt at t equals 0. Can you try for a couple minutes? Can you try first? Okay, so you can start taking the, if you want to take the tree diagram, but I think it's not too complicated, right? Because x and y only have one variable t. But we'll try first. I think mostly students are familiar with partial derivative, right? Okay. Do you agree, or you still have some problem with that? Just partial derivative. If you partially derive, for example, the z with x or y, it's supposed to be not too complicated. But now we include the chain rule. Okay, so we can start with the tree diagram. Z, x, y, and then this is just 1 like that. It means that the dz dt is, we can start with dou z dou x and dou dx dt plus dou z dou y dy dt. And then we start with, so dz dt is equal dou z dou x is 2xy plus 3y with power of 4. And dou x, okay, and dx dt is, remember, 2 cosine 2t. And plus dou z dou y is x squared plus 12xy cubed. And then cosine become negative sign. Okay, first we get, and then at t equals 0, we need to calculate x and y first. So at t equals 0, x will be 0, y will be 1, right? So we can see that this will be 0, this will be 1, this will be 0, this will be 0, and the whole thing will be 0. So 0 there, and we get, this will be 1, and then this will be 1. So 3 multiplied by 2, 6. So dz dt is just 6. At t equals 0 is 6. Okay. Okay, another example. Let's say we have w xy plus yz. Okay. Y is sine x, and z is e to the x. Find chain rule for dou w dou x. Okay. So this is not like to calculate like with a number, but to find the chain rule and the result of the chain rule. So the first one is not a 2 variables, it's 3 variables. So the branch can have 3. The branch can have 3, but the principle is still the same from the start, and then we find which one is the finish. Okay. Now this will be our tree, so W on the top, and then its branch become 3, so X, Y, and Z, right? X is just X, it's not branching anymore. Y, it's only one branch X, and Z also X, right? So that's it. So which means that the partial for the chain rule for the dou w dou x will be equal with C itself plus this multiply this plus this multiply this. So this is going to be dou w x plus okay, and then we can start to work out. So dou w dou x, we take is only y plus dou w dou y, it's x plus z, and dy dx is cosine x, and then we plus with dou w dz is only y, and then this is x, sorry, dou z dou x is e to the x. Okay, since y and x, y and z are function of x, so I think it's better to represent in variable x. So y is sine x, right? Plus z is e to the x, so x plus e to the x, and then cosine x, and then plus sine x e to the x. Okay. Or if you want, maybe sine x is e to the x plus 1 plus cosine x, x plus e to the x. Okay. This is the dou w dou x. Okay. And this chain rule is really powerful. Any variables, any branch, like 2 branch, 3 branch, 4 branch, if you increase more and more, still the principle is still the same. From the top, find a way going down. Find the path. You can have this path, this one, right? But I think this one is all after branching into 3, the rest is just 1. Alright. The chain rule also can help us to understand more about the differentiation in general. If you remember, we did the implicit differentiation before, right? Implicit differentiation. So let's take some review, okay, for this implicit differentiation. So let's write the, for example, I hope you still remember. So in calculus 1, we have the implicit, right? I think I also taught this before, but let me explain with the chain rule that we have learned. Okay. So let's say we have the implicit differentiation. So, for example, if we have an equation y cubed plus y squared minus 5y minus x squared plus 4, that's equal to 0. If we implicitly derive this, okay? For example, we take this and then we decide to take derivative for all these components. Do you still remember how to do it? Y cubed becomes, if we derive, y cubed becomes, no, not partial. Implicit. No, not partial, it's calculus 1. Y cubed becomes
3y squared.
Yeah.
dy dx.
Yes. Okay, so this becomes 3y squared dy dx plus 2y dy dx and then minus 5 dy dx. And then this will be minus 2x, 4 just a constant, 0, so this will be equal to 0. Now if we are going to find dy dx, what we do is we are going to group all the dy dx and then move the 2x to the side. So dy dx becomes and then that's the answer for dy dx, right? But since we have learned a new way to see the chain rule in the new way, so this is an equation having y and x, right? So we can say that it's a function of two variables actually. So we can see this as function of xy, right? Okay, and in calculus 1, we always taking that the y is function of x, okay? Which means if this is f, or maybe okay, so if this is f, maybe let me write maybe different f, maybe capital F to make it difference. Maybe this is capital F, like that, okay? So actually what we did is, we are taking from, but it's actually the same. Let me just write the same, okay? It's F. It is a little bit weird, but let me explain first, okay? So let's say we have F, okay? It's going to be divided branching into x and y, okay? But our y also f. This is what's really interesting in calculus 1. Y also f, okay? In which why we have this dy dx is basically because of the chain rule. So its branching become 2, but the y itself is function of x. So this is going to be that. So this will be dou f dou x. This is dou f dou y. This is dy dx. So if you would like to find dou f dou x, it means that dou f dou x plus dou f dy multiplied by dy dx. Okay? So here is dou f dou x plus dou f dou y multiplied with dy dx. Okay? So this is the whole derivatives. Which means now, in calculus 2, you can think this y and x, now you can think in partial. Like if you say, if we are partially derived with respect to x and y, then we can do that. To get this, so dou f dou x, so it means that dou f dou x then becomes, we derive with respect to x. It means that y is 0 now. Okay, so x will be only negative to x, right? Only negative to x. And then dou f dou y. Now the whole thing becomes 3y squared plus 2y minus 5, and x will be 0, right? So this will be 3y squared plus 2y minus 5. So basically we are equaling this equaling to 0, okay? And then we are going to solve for dy dx. So dy dx is basically negative dou f dou x divided by dou f dou y. So dy dx is negative dou f dou x, which is negative 2x, divided by 3y squared plus 2y minus 5. So the same. So we get the same conclusion. Okay, let me write in general what we did here, okay, in more general terms. Okay. So equation is, let's say, if x, y is equal 0, and x and y are, we define as functions of x. So actually the f, we can write f of x like that, okay, equal to 0. So apply the chain rule. So apply the chain rule. So this will be, actually we can also write dou x, this is dx, which is just cancelling each other, plus dou f dou y dy dx. So in turns that dy dx is negative dou f dou x over dou f dou y. So this is another way to look at the implicit differentiation in calculus 1. Okay, so we can rewrite in terms of function of two variables. So we can take it's become more whenever you have like a function f like this xy is we can equal that to 0, and then we can derive partially x and y. Then we can put here partial x, partial y, and then that's the result. Okay. Maybe giving you another example to look at. Okay. And actually, you still can choose how to solve the implicit. Okay. We can take this, or we can take directly. Okay, we can take directly. Okay, let me give you another example, okay, to feel how this going to how it's going to work, okay? And how are going to which method we're going to use. So example, let's say we have let's try 3 variables, okay, 3 variables. Can we still do that? So let's say we have x squared plus y squared plus z equal 1. If z, we define z as a function of xy, okay, then compute dou z dou x and dou z dou y. So I think we can start to see the function, the whole function, the 3 variables is let's say f, okay, f, the big F, and then we can have x, y, and z. X, y, I think we don't have any branch, right? We don't have any connection, so we only have z. Z has another x and another y. Okay. So this will be dou f dou x, dou f dou y, and dou f dou z. This is dou z dou x and dou z dou y. So to find dou z dou x, we start from f and then we are going to x. Okay, so we are going to end on x. So dou f dou x plus dou f dou z and dou z dou x. And this is equal to 0, okay, equal to 0, based on the equations here. So maybe we can write here, let fxyz is x squared plus y squared plus z squared minus 1. Okay. And then we derive this, and the constant will be gone, right? The constant will be gone. So dou z dou x is negative dou f dou x divided by dou f dou z. So basically, we are going just to partially derive with respect to x. So 2x, and this will be 2z. So it's just x over z. So minus x over z. Okay. And for dou z dou y will be similar, and you will see that this is actually taking this over this. Maybe let me move this to this side here. This is going to be there, and this will be this plus this. Okay. I consider this the first method. Okay, the first method. The second method is the one that you did in calculus 1, but we can apply the similar approach in calculus 2. Okay. Let me write again the formulations: x squared plus y squared plus z squared equaling it to 1. So we are going to directly derive this, let's say with partially to y. But when we did this, if we are taking implicit way for y, so every y we can treat them as usual. So y squared becomes 2y. Okay. For z, because z is function of xy, then this will be 2z and then dou z dou y. Okay. For x, 0 as a function. Okay. So this will be 0 plus 2y squared 2y plus 2z dou z dou y is equal to 0. So dou z dou y is, we move to the right, this will be negative y over z. Okay. If we derive with respect to x, then x will be a regular one. So x become 2x and y become 0. But z, since z is function of xy, so 2z and then dou z dou x, this is equal 0. So dou z dou x become negative x over z, the same. Okay, so this is the second method, the direct approach. Either way, the same. Okay, the same way, the same results. Okay, I think that's will be the end of our lecture. Okay, up until the chain rule, we have time. We can have more exercise later. But I think next Wednesday or Thursday, we are going to have a small review on midterm preparation. Okay. Any questions about this? And it is quite practical, right? The more you are familiar with its techniques, I think you'll be able to solve the most general problems. Okay? So this is implicit differentiation in chain rule. So if you think the chain rule in implicit is always having, for example, here you see that it's always repeated itself. Like the functions is having another functions. So it means that what I mean is, if you want to find dou z dou x, we need to find this, right? But this is actually dou f dou x, okay? Because we define it implicitly. Okay, that's the interesting part on implicit. Okay, and this will be the, let me check.